Good afternoon, everyone. Thank you for joining us today and welcome to the next webinar of the World Value Survey Association. We are very pleased today to have with us Liwei Jiang, who is a research scientist at NVIDIA and who recently defended her PhD in computer science and engineering at the University of Washington. We congratulate Liwei with this important milestone in her professional career.
Thank you.
Liwei's research focuses on AI safety and alignment, on natural language processing, and human-centered AI, with a particular emphasis on building AI systems that genuinely benefit the humanity. Today's talk is titled, Can Language Models Reason About Individualistic Human Values and Preferences? And Liwei will examine today whether language models can understand and predict individual human values and preferences based on broad demographic categories. So this presentation will include IndieValueCatalog, which is a dataset based on the World Value Survey, and also discuss what it revealed about pluralistic alignment of AI, moral diversity, disagreement, and the limitations of current frontier language models. Liwei, thank you very much for joining us. The floor is yours.
Thank you so much for the kind introduction. Yeah, hello everyone. I'm Liwei, and today I'm super excited to talk about my paper on can language models reason about individualistic human values and preferences. And this work was published at ACL 2025 last year, and it's in collaboration with my collaborators, Taylor, Sydney, and Yezhen. All right, so before I talk about the paper itself, I want to first give a little bit of the overview of the AI alignment problem in general. So alignment problem has been a problem that exists for quite a long time. And there are many different definitions of it, but all of them points to the core social technical challenge about teaching AI human morality, values, and needs, despite their complexity, contradictions, and evolution. And here, this alignment problem book is one of my favorite books that talks about this problem. So I call it a social technical challenge because although that it involves AI and it involves model building, but a lot of the core challenges of how to teach AI is really grounded in our society. And alignment is not a new problem in AI. And in fact, it has been a mission impossible for more than 70 years. And over time, we've moved from philosophy to theory to these large-scale systems and from abstract logic to real-world high-stake deployment. But the rise of large language models has fundamentally changed the landscape by bringing alignment into the real world. Since the release of ChatGPT in late 2022, now roughly 1 in 6 people uses LM-powered AI tools, and for the first time, AI systems are directly interfacing with real humans in their everyday lives. And beyond skills, this also marks the very first time that AI has achieved truly global reach. And as a result, AI now faces diverse and often conflicting expectations across cultures and social contexts. So now that we've seen a little bit of these conceptual definitions of alignment, so how does it work in practice? So let's take a brief review of how alignment works in this technical side. So LMs, they typically go through 3 stages of training, including pre-training, supervised fine-tuning in the middle, and then reinforcement learning. So for all the models that we are currently interacting with, for example, ChatGPT, all of them go through these 3 stages. And in pre-training, the model learns from massive web-scale data for training. And they use this next token prediction learning objective to capture a broad distribution of the text space, and to learn that what kind of text can be the possible continuations. And in supervised fine-tuning, the second stage, the models is trained on high-quality responses. And then it will shift the probability mass of the model, the base training model. towards these more helpful and structured answers, and then it will narrow the output space. And finally, we have this reinforcement learning stage that pushes the model to maximize the reward while staying close to the supervised fine-tuning anchor that will further concentrate the probability around these high reward modes. So what does it even mean here? So we can see there's a demonstration and the reward. And supposedly that the demonstrations and reward functions, they would capture what we hope to achieve in this alignment process. So what are they exactly? So nowadays, the AI systems are mostly operating on top of this concept of alignment based on human preferences. So human preferences is pretty abstract, but in the context of LLM alignment, what it means is that we give this different input, the situation to the annotators, to the humans, and then the answers from the models to the humans as well. And the humans will give a thumb up or thumb down in terms of whether this response is a good answer to the specific question that's given to them. And one example is for the situation. So if the situation is telling a lie to protect a friend's feeling, and then some people, they may say that we should always be honest. So the situation is bad, so we give a thumb down. But some other people, they may think that it's actually good to help a friend, so they give a thumb up. So we can see that when we're operating this human preference, the alignment through this human preference lens, and then people actually have disagreements sometimes. And but for the model to learn the signals, and when there's roughly the same number of people who agree or disagree, and in the end, the model will learn an even out, average out version of these ratings and just turn the thumb up and thumb down into neutral in this case. And here's another example where the situation is wearing a blue shirt, and then some people say, oh, it doesn't matter. And some people, other people say it's either way. So both people are neutral to this case. And in the end, when the model is learning, and then the average rating is also neutral. But are these two cases the same? So both the model learns as neutral, but obviously they are pretty different. In the first case that we do see that people have disagreement, and in second case is when people are having their consensus to be neutral to this case. And actually, in the first case, it could be pretty problematic to end up with a neutral label because we don't really capture the fine-grained raw labels from the individual peoples. So this is why we need to consider value pluralism in AI, and which is the philosophical view that different judgments or human decisions can be supported by multiple potentially conflicting human values at the same time. And there are moral cases that are fundamentally not reconcilable or irreducible to a single judgment. And beyond human values, there's also other types of important considerations, such as human rights and duties, all worth considering through this value pluralism perspective. So in terms of value pluralism in AI, so it has become a very popular topic, very important topic as well, since that we first brought up this concept with my collaborators, Taylor and many others in this position paper, Roadmap to Pluralistic Alignment. And in this paper in particular that was published in ICML 2024, we operationalized to the different definitions of pluralism. So for example, overtime pluralism means that we hope that the output of the models would have a good coverage of different perspectives. And steerable pluralism means that we hope the model we are able to steer the model towards different directions if we desire to. And also distributional pluralism, where the model's underlying distribution towards different opinions we hope that they ideally map the real world distributions across the globe. So this overall direction points to this important question of how do we build AI for this diverse need of everybody, of all people. And in reality, when we operationalize pluralistic alignment, a lot of the time, we can't really capture the fine-grained distinctions between people. And because it's just very hard to get to individual level of data. And what people then ended up do is to identify these high-level categories of latent variables that people can defer on, and then use these different aspects to capture the differences between people. So it is definitely a step forward compared to just treating everybody as the same identity, but there's could be some problems here. So for example, if we're taking personality as one dimension to measure people's differences, and then this is the big five personality dimensions, we ended up, we'll put everybody, the crowd of people into these buckets. So people are gonna be categorized by some type of personality. So still that we have some level of distinctions between people. There's variation for capturing people's differences, but we ended up sorting people into bucket, which will also create these stereotypes for when we are interpreting different people's opinions. So this calls for a urgent question about how can we take us even more step further to move beyond this core sense of diversity to more fine-grained sense of individuality. So this leads to our research question of, can language models reason about individualistic human values and preferences? So to answer this question, we need data in a certain type. So specifically, the most ideal type of data that we hope is for, first of all, definitely the value laden question should be posed to real humans. We cannot really use synthetic data, which is very popular in the AI space right now. For the real human data, ideally, we want a series of one person to answer a long sequence of questions that can probe their value preferences from different perspectives. And ideally, we also want to collect such long sequence of data from lots of people. So that will give us a good sense of how one person's values systematically emerge, and then how the different peoples are differ from each other. So that's the type of data that we want. But in the AI space, we don't actually have such a lot of data like this. So even when nowadays people are training the models at very large scale models with very large scale data that are somewhat curated from humans, but usually the case is for each question, we're collecting a couple of humans annotations, and then for one person, we don't really have this catalog of questions that all annotated by the same person. So that's not very helpful. So existing data is not very helpful for answering this question. But luckily, we have work value survey data. So as we all know here, the work value survey capture this rich data set that have lots of respondents across the globe, and everyone has this long sequence of very expressive set of question answers, so that it can be used to understand how each individual is expressing their values, and also how the different differences across individuals, across different regions, across different demographics around the world. So that's what we used for studying this question. So we also did a little bit of conversion of the raw world value survey data to fit the language model schema. So original world value survey has these multiple choice questions, and then Likert scale questions, rating scale questions, and also ranking questions. So they're in very heterogeneous and expressive forms. And for us, because we want to have a more unified form of data, and also in language form, to really see how language models are able to reason or tell the differences between people's value profiles. So we convert the raw questions in world value surveys into these statements that form what we call as an IndieValueCatalog. So we map the original questions answer options into these natural language descriptions that express the similar trend and skills of in terms of the answer dimension. So for example, here the raw question is a Likert scale question between 1 to 10, and 1 is completely satisfied. So we map 1 and 2 to very satisfied, while 9 and 10 to very dissatisfied. And then we also group the statement differently, one in a very refined manner where we tend to have at least 4 to 5 statement options per each question, and then more high level coerced way of grouping by grouping the statement into polarity. So in that case, 1 to 5 are all mapped into satisfied. So for each individual, we ended up with these 253 value expressing statements. So each person has a set of statements that express their values in this natural language state, in natural language. And then there are about 93K of this real human data that we ended up using in this world value survey, converted from world value survey raw data. So in addition to this value expressing statement, we also collected this demographics declaring statement, which are the questions that ask about this metadata about people. And we ended up with 31 of these demographics declaring statements as well. So that gives us very great resources for evaluating models. So the way that we evaluate the model is for each person, so here person A, we segment the data into a portion that we provide to the model. So these are the known statements of that person. And then the model will read all of these statements coming from person A. And then the model will also be given a new question and the set of statement options associated with that question. And then the model will give a prediction of which option of these statements will most likely to be said or to be produced by person A. And then basically based on this known statement of the person to guess what they would likely to say in a new question. And then we calculate this accuracy of how accurate this model is predicting that specific person's statement based on the gold labels from world value survey. And because there's so many individuals data in this data set, so that we're able to test the model across different people. So we just repeat this testing process with another person, many different people in this data set. And we also took a cross-validation setup that we have these 3 different ways of partitioning the data into demonstration set and probe set. So there are 3 setups of having demonstration, 200 demonstrations and 39 probes. And in order to cover all these different question categories, so we take 3 questions per each category. So this will give us a more generalizable result because it doesn't get so impacted by the particular choice of the probing set of questions. And then for this evaluation, we also we randomly pick 800 of individuals sample from the data set and then use them to evaluate different models. So here is the result of how well the model can predict the individual's judgments. And then we can see, so this is a study that was done last year. So it's these models are the frontier models back to 2025 or before 2025. But nowadays, I think there's not so much, might be a little bit more stronger performance right now, but still there's a good gap in terms of the performance for the most recent models on this evaluation suite. But we can see that across these different dimensions of questions and also the overall questions, the models are able to guess the statement about between 50 to 65% of accuracy. So it's not very, very strong, but definitely stronger than random, which means that one person's sequence of statements does inform the model to learn some patterns of their value preferences, value profiles in general. But it's not very strong with these off-the-shelf frontier models. So another aspect is if we're breaking down of the test respondents data into these different regions, or breaking them down by finer grained demographics dimensions, and then we can see that the different models performance across the different dimensions of demographics informations is different. So from here, for example, the predictions on Oceania people are having better predictive power, and then for North American people has better predictive power. But then when it comes to African or Asian or South American people, and then the predictive powers are lower. And similarly, for higher income people, the model's predictive power is stronger. Accuracy is stronger, and versus low income, it's a pretty much lower compared to high income. And similarly, for these different social classes, we can see upper middle class is the most well predicted category. So there's definitely some variations across different demographics groups in terms of models' predictive power. And then we can see there's some inequity between these different groups. So we want to quantify how models are now able to predict them in a equal, have high equity power. So here we quantify this measure as using this inequity score. So what it does is basically it takes the variances of the model's performance across the different demographics dimensions, and then the higher the variances means that the model has more unevenness across different people, different groups of people, which means that it is more has more inequity. So the lower the better of this score in terms of the fairness of implication of the models. So we can see that these are the proficiency of the model's prediction versus the equity aspect are actually two orthogonal dimensions, because we can see that for some models, their proficiency score is pretty high, but their inequity score is actually also pretty high, which means that they are consistently doing very well predicting in certain demographics of peoples, and then consistently doing pretty bad in some others, but it will average into a pretty decent score. So yeah, the proficiency and inequity scores are definitely lie on orthogonal dimensions. And another test that we did is we are wondering if we only use the demographics information, remember we have 31 of these demographic statements versus this value expressing statement. How are we going to get different predictive power from the models? So here, the red line, dotted line here is the model's performance when we only use demographics statements as the null statement to the model. So we describe the people only by their demographics. And then these, the green box here is we only describing a person based on these value expressing statements. And then the orange box here is we describe a person based on both their demographics information and also their value expressing statements. And then the x-axis here is how many of the value expressing statements that we include for informing the model about a person. So we can see that with only the demographics expressing statement, and then the model is able to do pretty decently in terms of making the prediction. But when we are giving more of these value expressing statements, and then the models are able to know more about a person, if we're given more numbers of these value statements to capture more comprehensive picture of one's value preference profile. And then the best case will be combining this value expressing statement with the demographics declaring statement so that both information are complementary to each other for the model to understand their fundamental underlying value profiles. So we can also know that because the demographics itself is not able to give us as high of a prediction power compared to using these value expressing statements, which also means that if we only study differences between people or operating on top of the assumption that people are different by their demographics, as a lot of the current pluralistic alignment works are doing, and then we do get the risk of stereotyping people based on the group-based interpretations. So far, all the analysis are done by these with off-the-shelf models. Off-the-shelf just means that taking any models out there that we don't customize them and then evaluate those models as is. So the next true question for us is, what if we can train models that can reason about the individualistic values instead of just relying on the models as is? So we did that. We trained the models. We randomly sample 1.6K of people from this global individual pools, and also, of course, balanced across different regions, different geographical regions. And then for each of the person, they have 253 questions per person. So we actually get quite a lot of actual training data by having 253 times this 1.6 people. So of course we can include more people because in overall there are 93K of people, but training these models are actually quite costly in terms of time and also computational resource. So we ended up able to train on this many, but further scaling would help. And we have some further results to show that scaling up by the number of people's data will further teach the model to better understand across individual preference patterns. So for this example training data, so essentially still we're providing this null statement from a person, and then for a left out question, we provide the number of options that capture those that question capture the question, and then the model will learn to predict which option is from that same person who's producing this null statement. And our results show that we are able to train the models to do better in terms of reason about these values compared to not trained models. So here zero shot means that we just use the off-the-shelf model. And this is, I believe, Llama 3.1 AP model back then. That was the popular one to use back then. And then the IndieValueReasoner model is the one that trained on 1.6K of people's data. And then this ensemble baselines, these are basically baselines that are based on the statistics among the entire data set. So among the data set with 93K of individuals. For top one, we just mean that we go in and go into the data set and then find the person who share the most number of same statements with the person that's being tested. So the basically this baseline answers the question based on the most similar person in the data set. And then for ensemble, this cluster one, which means that we not only take the most similar person in the data set, but we take the top n most similar person in the data set, and then take the majority vote among those people, so that it's less prone to the noise from the top one choice. And here the n, the size of the cluster is 24, which is the best cluster performance that we gather when we try different n's, which means it's a pretty strong baseline, statistical baseline here. But even compared to the very strong statistical baseline, the trained model is doing very well. And also it's notable that the different statistical baselines are based on all the data from 93K of people, but the IndieValueReasoner model only has seen data from 1.6K of people. So it's definitely, it's pretty sample efficient. And we can also see that when it comes to the inequity score, and then the trained model has decreased inequity score, which means that it learns to predict, have more even, more fair predictive powers across different demographics of populations, which is good. And then we can also see that the more individual data that we use to train the model, and then the better, the stronger this model gets to learn how to make predictions. So yeah, it's just saying that this orange curve has the model to train on the most number of individuals, and then the performance is going higher compared to the others. Yeah, this is just some other test cases where we also try to mix in different ways of presenting these known statements, show different numbers of known statements, and then combining with the full set of known statement, the full 200 demonstration set, and then turns out that having different number of known statements to teach the model is the most effective for having the model to infer different variations of one's value reasoning patterns. And another test that we tried is we also train models only based on data coming from this different continent. So train a model that only, so the y-axis here are the models that trained specifically on the population from certain continent. So there's African specific model, Europe specific models, and so on. And then we also tested these models across the held out individuals from different regions as well. So we can see that is definitely the case where that the models, the region, the continent specific models does work very well on the content specific test set. But there is one outlier here where the model, the Oceania model, the model that's trained on Oceania data, it doesn't really do well on the other test bed, except the Oceania test set. And then it's also the case where this Oceania test set is relatively easy to all these different models, but still, for example, the geographically far away models, regions are not doing super well. So even the Oceania data seems to be quite easy across the globe, but the Africa specific model is not doing very well on the Oceania data. And yeah, all of these models are trained on the same number of individuals from these different geographic regions. So why is that the case here? So we just look into the statistic of the individuals' data in across different continents and found that so because Oceania data is mostly coming from New Zealand, I believe, and it doesn't have the level of varieties and diversities to really capture the global the diversities across global populations. So in another word, that Oceania data is more homogeneous in general, so that it's easier for predicting for the models. And and the model that's trained on this data is not able to capture the differences across these other populations. So another interesting thing here is we can see, for example, this North American model. It does well on this its own North American test set, but it's also doing pretty well on the European test set, and it doesn't do as well on the African test set. And in the South American case, it's doing pretty well on South America and then North America because they're geographically adjacent to each other, although still different. But it's not doing very well on African or Asian data. So yeah, there's definitely some correlations between the models that train on certain geographic correlation and then the geographically relevant test sets to those regions. And yeah, so that's most of the analysis and results that we did in this paper. And yeah, thankfully that we ended up using World Value Survey for running this study, and then we don't need to collect our own data. And this data is so rich, and we are only using a small portion of it for training the model because of the cost of computation. But I really believe that we can push a lot further for scaling up the training and also use this really, really rich real human data to inform our understanding of the current AI system and also inform the design of the next generation of the models. Yeah, so thanks so much for listening, and I'm happy to take questions.
Thank you very much, Liwei, for the very interesting presentation. We are very happy that WS data has been useful. So the floor is now open for questions. You can post those in chat or you can raise your hand and speak up, whatever you prefer. And while everyone is thinking, I wanted to share one observation. In particular, when you were showing this table with the share of correctly predicted responses by WS questions block or section, models seem to do much better on sections such as, yes, happiness and well-being, and among the other also ethical values and norms. And some of the specifics of these questions is that many of these questions, I don't want to say that responses are very homogeneous. There is some variation, but they're very all largely skewed to one side. So most people say it is not justifiable to break the law. It's not justifiable not to pay your taxes, etc. So mostly they're skewed to one side, and on happiness and well-being, they're mostly skewed to the other side. So many around the world say they're happy. And I was wondering if there was, well, on the other hand, if you compare, for instance, with political interest participation, there is much, so the percentage of correct guesses is less because there is much more variation around the world about what people think about democracy, voting, or signing a petition. And if you established if there is any association between the distribution of this in people's responses and how successful the model was with guessing it correctly.
Yeah, so I also observed that the questions, although they are having these different categories, and then within the category, some categories have more similar questions, and some are more just added spectrum. So yeah, so it's definitely the case that if the questions are capturing very relevant or similar aspect of the values, and then the models would also pick up on that and then learn the consistencies of a person's answers across similar questions. And yeah, so I think it's very interesting to have a quantitative kind of observation here that some categories are actually much more predictable compared to the others. So I think it's good to it's almost like a model-based data analysis of the value survey data as well to so for us, we run the study because we're interested how models are performing. But then if we fix the model side, and then this is very interesting to reveal how the data, the survey is designed. So yeah, I think it's kind of like bi-directional, very mutually informative. Yeah, this is a very great observation and question. Thank you.
Thank you. We have a question from Daniel Capistrano, who is our co-PI from Brazil.
Thank you, Xenia.
Nice to meet
and
you.
thank you, Liwei. Thank you very much. Super interesting work you've done there. Maybe I have missed it, but I wonder if you have looked back at the inequity in relation to social class, apart from looking at the variation across continents. And the second question would be, have you tried to have a look at as well in relation to separating English-speaking countries and non-English speaking countries, just to get an idea whether like this is a language issue, the inequity is perhaps related to the training data or something like that. Thank you.
Yeah, that's a really great question. Thank you for the amazing question. So I did look at I think I look at there are 31 demographics questions that we used, but I think I used around 25 or 28, between 25 to 28 of those the demographics questions, and then run the breakdown. So these three are the demonstrations. I included the analysis of the rest of the dimensions in the paper as well. So if you're interested for checking on them. So for this inequity score, it's actually averaged across all the 20, 25, 28 dimensions that we are looking at. So this variance is considering all these demographics dimensions beyond these three. Yeah, and then in terms of English speaking or not, that's actually a very great question. I didn't run the analysis based on the language, but it might be that it could be the case because we can see that some like African region and Asian region are consistently just having the humans, the tests that are being consistent more challenging, which means that these people population from these regions are more harder to predict. And but in terms of language itself, I think like North America and then Oceania are also both kind of speak English, and most of the participants, I believe, are all most of them are also speaking English, but they have very different distributions. I think it really boils down to how heterogeneous are the populations in those different regions for really informing the model to learn a spectrum of people. Yeah.
Thank you very much, Levi. We have one more question from Henrik Doppel. Henrik, do you want to say your question? Or should we read it? So in genetics, which is similar hypothesis-free data-driven work, we also find that GVAS hits cannot be transferred very well to other populations' cultures, so individuals from there cannot profit from recent development in personalized medicine. So your weird model predicts well in other weird samples. What does a low predictive power means in your case?
Yeah, that's a good, great point, great question. So here the predict power basically means that if the model is trained on a sample of training models and how well it's able to predict on a test set. So how much accuracy does it achieve on different test sets? So here, so the weird models, I think pretty representative one is maybe the North American model. And the European models are more the like weird models here. And then it is totally true that these models learn from these populations are doing the best across the European and North American populations. And so I think for the model to learn the best, it will need to learn from all populations across different regions. So here we also have this overall model. The overall model is doing the best in this overall test set. So the overall test set contains population across the entire continent categories. And then the overall model is doing the best on this basically across all the populations, meaning that it's very important to consider the comprehensiveness or the span of the inclusiveness of the data itself for training a model. In any kind of training, for us, we train this reasoner model, but in general, even chat-based LLMs, and then we still need to really need to consider the pluralistic aspect so that the model wouldn't be just prone better at certain questions compared to the others. Yeah.
Thank you very much. So we have a couple more minutes. If anyone has a question that you would like to know about AI and its approach to values, please post it or raise your hand to speak up. And while everyone is thinking, I will have another question for you. So the paper, I read your paper, thank you very much. So the paper argues basically that demographic categories, they can flatten this value individuality. But from a lot of research in social sciences, we also know that some demographic dimensions, they still do structure values such as education or age or social class. So how do you recommend the researchers should balance these two conclusions?
Yeah, that's a very great point because we also see that here the demographics information is very strong. So we have 31 demographics information here, and it's almost the same predictive power of 50 value expressing statements. So yeah, you might think 31 and 50 is not that big a difference, but in like this is all like in context learning of LM. These are actually quite different numbers of examples. So and which means that these demographics questions, they're very descriptive, they're very expressive, and probably more obviously representing a person's profile compared to these value statements. Because if I didn't really run that experiment, but with 31 of value expressing statements, it would have most likely to have much lower score. So it's definitely lower, but where it is, I'm not sure, but anything between 55 to 60. So yeah, the demographics dimensions are the strong ones, but it's better to combine those with additional, more latent, more implicit value descriptions to describe a person. And the complementary kind of power comes in to best teach the model. Yeah.
Thank you. So we have two more last minute questions. Would you say the source of differences in predictive power across groups or continents are due to inequalities in training data, fine-tuning, or RL? And how do LLM deal with age, period, and cohort analysis? Because values are largely cohort-driven. What you see, however, is age in the data.
Yeah, so for the first question, it's my intuition is it's mostly coming from the training data itself because fine-tuning or RL fine-tuning is very standard and all the models are fine-tuning the same way. But when we're swapping in different training data, we see a big difference in terms of their downstream performance. And then we didn't do RL for the reasoner model training here. But overall, if we are considering the general LM, it's also the case that across different companies, even their training recipes, like methods and their RL design are very, very similar. But what really makes the difference is the training data. And if it's in reinforcement learning, and then it's the training data plus the reward signal. So data itself, reward signal basically come from the training data of the reward model. So a lot of these are really, really data driven. And then in terms of age period and cohort analysis, so is age period here means that different waves of the model, or what does wave period mean here more specifically?
Period, yes, means the period when the data was collected.
I see. Yeah, definitely. I think there will be a difference here. We didn't consider that for running our analysis, but I would imagine that the data that's collected before, for example, before 2000 versus the wave that come in 2022, people have more different ways for, like, by large, more different statistics across different questions. So yeah, but that will be an interesting analysis study to run too. Thank you for the question.
Thank you very much, Levi, for a very interesting presentation. Thank you very much for joining us today. If you have any questions, I hope Levi doesn't mind, you can follow up by email. We wish you the best of luck in your future research, and hopefully the next wave of the WVS will also be one of inspiration. We are working now very hard to collect data in as many countries as possible. Thank you very much. I wish you a nice rest of the day and hope to see you joining us for the next WS webinars. This one is recorded and it will be also available at our website. Thank you, Levi.
Yeah. Thank you so much. Thank you. Thank you for creating this amazing resource. Thank you.